Controlled Environment Plant Production Engineering Technology Education modules are developed and presented by The Ohio State University, Rutgers, the State University of New Jersey, and the University of Arizona, with support from USDA, NEFA through their Higher Education Challenge Grant Program. In this module, we'll discuss the topic of sensor calibration theory. This module is presented by Dr. Peter Ling of The Ohio State University and Dr. A.J. Both of Rutgers, the State University of New Jersey. This module focuses on sensor characteristics and the need for calibration. To learn more about the methods of sensor calibration, please take a look at the Sensor Calibration Practices module. This Sensor Calibration Theory module will allow you to meet 5 objectives. By the end of this module, you will be able to list considerations necessary to ensure good sensor data, explain why good sensor data is important, describe instrument characteristics that are important for calibration, explain why multiple data points may be required for proper calibration, and identify quick check values for light, humidity, temperature, and CO2. The first objective is to list considerations necessary to ensure good sensor data. Sensors provide us with a numerical value that represents the environment around them. If the environment is filled with a variable mix of qualities, then the sensor will output a numerical value that represents a variable mix of qualities. In other words, the sensor does not have a filter. If we put garbage into a sensor, then the sensor will give us garbage out. There are several things we can do to ensure that we do not get garbage from our sensors. First, make sure the sensors are located in an area where environmental conditions are representative of the entire measured environment. The sensor should be located where we want to measure. When measuring a large area such as the inside of a greenhouse, it is important that there is sufficient air movement to blend the temperature, relative humidity, or carbon dioxide to ensure a sensor output representative of the entire greenhouse. Second, we need to ensure that there are no confounding factors affecting a sensor's ability to accurately read its environment. The sensor must be free from direct radiation. We have observed, for example, that a temperature sensor exposed to direct sunlight through a building window can read as much as 41 degrees Fahrenheit higher than a shaded sensor next to it. The sensor should not be near any thermal sources such as heaters or thermal storage media. A ground potential difference occurs when a ground in one area is at a different voltage than the ground in another area. In a network of sensors that are all connected to each other, this voltage difference can cause data errors. Continuing with things we can do to ensure that we get quality data from our sensors, it is important to choose a sensor appropriate for the job. Sensors have different ranges, resolutions, linearities, and are designed for usage within specific environmental conditions such as a certain temperature, humidity, and CO2 range. Later in this module, you will be able to see what range, resolution, and linearity look like. Decide which sensor is the most suitable for the intended application. Whether voltage or current output of a sensor is preferred depending on signal transmission distance and costs. Typically, current output is preferred for data transmission of longer distance. Finally, there is sensor calibration. Calibration is the focus of this module. Ensure that measurements are close to true value by using sensors that have been properly calibrated. The images to the right represent 2 different CO2 sensors, reading side by side in a homogenized sample of air. As you can see, the readings differ by 82 parts per million. This difference may be due to a lack of calibration. Why is good sensor data important? The control system must activate and deactivate cooling pads, supplemental CO2, supplemental lighting, vents and shade curtains, heaters, and exhaust fans when needed for optimal plant growth. Plants depend on this control system. and the control system depends on sensor inputs. Properly calibrated sensors ensure that greenhouse conditions recorded are truly representative of the environment. There are many sensors in the greenhouse that need periodic calibration to ensure optimal environmental control. Sensors that monitor the aerial environment include CO2, humidity, light, temperature, and wind speed. Sensors that monitor the root zone environment include dissolved oxygen, electrical conductivity, pH, and soil moisture. Other sensors can be used to monitor static pressure, which is used to check exhaust fan operation and double poly inflation. Objective 3 is to describe instrument characteristics that are important for calibration. These characteristics include accuracy, precision, linearity, resolution, and hysteresis. Accuracy is the deviation from the true value. Precision is when repeated measurements result in similar readings. Linearity describes direct proportionality between output and input value. Resolution is the amount of detail contained in the measurements. And hysteresis describes how output is dependent on the direction of input change. In the next few slides, we will discuss accuracy, precision, linearity, resolution, and hysteresis in greater detail. Let's talk about accuracy. The exact measurement of an object's true value is not possible. In other words, it's impossible to be perfectly accurate. This is because it is impossible to hold all variables constant when taking a measurement. The inability to obtain an exact measurement of an object's true value compels us to introduce the concept of error. Error is the difference between the measurement and the true value. And of course, since true value is unknowable, so is the exact error. So you may be aware that with every sensor, the error is reported. So how is this error figured out? The solution to figuring out error is to repeat a measurement process many times in the same conditions. From this, a random variation of values will be generated. From this random variation, we can assign a numerical value to the error for future measurements. The error may be expressed as an absolute or as a percentage of the measurement range. The true value will lie within the range of error. How is accuracy increased with calibration practices? While calibrating an instrument, parameters with the greatest effect on sensor readings are held constant. This reduces error. An example of this is calibrating a temperature sensor while keeping it shielded from direct radiation. Direct radiation has a great influence on temperature measurement. Another example is calibrating a relative humidity sensor. Temperature is a parameter that must be held constant because temperature has a great influence on relative humidity. Calibration conditions should match use conditions. Calibrate sensors in an environment similar to where they will be used. For example, if an instrument is going to be subjected to vibration, subject it to similar vibration during the calibration process. This is important because vibration can reduce the effects of static friction. Calibrate sensors for as specific a range as possible. For example, Type T thermocouples are typically rated at plus or minus 1 degree Celsius accuracy. By calibrating its response for a given temperature range and environmental conditions, the accuracy can be improved to plus or minus 0.5 degrees Celsius. Application-specific calibration makes sense, especially when the sensor is nonlinear. A general calibration of the full range is laborious and requires many data points and a statistical regression. For a narrow range, however, the sensor response can be approximated with a linear function that can be determined with tighter precision. Thermistor output, for example, is nonlinear. A calibration that is application-specific with an especially narrow temperature range could improve its measurement accuracy. Let's talk in detail about precision. Precision is a small deviation among data points. In other words, when the same measurement is made in the same conditions multiple times, each data point will be close in value to all the others, if the instrument is precise. This contrasts accuracy in that accuracy is a small deviation from the true value. Accuracy is how close a singular or group of measurements are to the true value. These bullseye images will be used to represent the differences between accuracy and precision. We will take 4 shots at each bullseye. If the shots are all very close to each other, we are precise. If the shots as a group are all close to the center of the bullseye, then we are accurate. We take 4 shots at the first bullseye, and you can see that the grouping is very close together. This is precision. However, the grouping is not near the center of the bullseye. This is not accurate. We take 4 shots at the second bullseye. Notice that the 4 shots are not grouped very close together. This is not precise. However, the average of the grouping is very near the center of the bullseye. This is accurate. We take 4 shots at the third bullseye. This time the shots are grouped very close together and their average location is very near the center of the bullseye. This is both precise and accurate. We take a final 4 shots at the last bullseye. This time the shots are not grouped close together and their average is not near the center of the bullseye. This is neither precise nor accurate. If a measurement device is precise but lacks accuracy, then sensor calibration will solve the problem. One can determine an offset value of the measurement and use the constant to improve the sensor's accuracy. If a device is not precise but accurate, then data averaging could be used to reduce uncertainty of the data, provided that the error of the data has a normal distribution. Statistically speaking, the measurement errors must have a normal distribution. If an instrument is both precise and accurate, it is not necessary to do anything. If an instrument is not precise or accurate, there may not be much that can be done. It may help to perform a sensor calibration and data averaging simultaneously. Let's talk in detail now about resolution. Starting at an arbitrary value, there will be a minimum signal input change, below which there is no change in output value. This minimum value is the smallest measurement change and is called the instrument's resolution. Resolution can be reported as an absolute value or as a percentage of the full scale value. Note that an instrument with a large hysteresis does not necessarily have low resolution. A sensor whose readings are greatly dependent on the direction of change may still be able to display small changes in the measurement value. Here are 2 graphs that we will use to visualize resolution. Arbitrary values representing sensor input are on the x-axis and output values are on the y-axis. Let's see what it looks like as an input value increases. It takes a specific change in input for the sensor to respond with a new output value. This distance, shown in green, is the resolution. Now let's see the graph of a sensor with higher resolution. The resolution is now represented by this distance. On the blue graph, which is representing a sensor with higher resolution, a smaller change in input triggers a change in output value. The lower resolution sensor does not have as much detail. With a higher resolution sensor, it is possible to get a more detailed measurement. The high-resolution sensor on the right can register a 0.5 increment change in input, while the lower resolution sensor on the left can at best register a 1 increment change in input. Let's talk in detail about linearity. Before we do this, I want to make sure that we understand the difference between input and output values. An input value is the correct or true value existing in the environment. The input value is the stimulus for the sensor. The output value is what the sensor measured. The output value is what shows up on the display for the user. Some sensors exhibit direct proportionality between input and output values. This direct proportionality can be described as a linear relationship when input and output values are graphed. This linear relationship can have either a zero or a non-zero y-intercept. The images to the right represent input values on the x-axis and output values on the y-axis. Other sensors exhibit a nonlinear relationship between input and output values. This can be seen on the graph on the bottom right corner. Choose sensors that are linear in the range of use. The graph shows a typical thermistor response curve. Resistance is on the y-axis and temperature is on the x-axis. This is a good sensor for the greenhouse because it is approximately linear in the range of use. For temperature inside the greenhouse, we would expect to see the temperature around 18 degrees Celsius. Although this sensor is nonlinear over its entire range, it can be approximated with a linear function within the expected range of use. In this particular case, if the temperature rose much above 50 degrees Celsius, the temperature sensor would be inaccurate using this linear approximation. However, we do not expect to see temperatures above 50 degrees Celsius in a greenhouse where temperature is being monitored and controlled. Working with linear functions makes working with the sensor less complicated. Lastly, let's talk more in detail about hysteresis. Friction of an instrument creates lag between input and output. This applies both to mechanical and electronic sensors. The output value is dependent on the direction of change of the input. When input increases or decreases, internal friction delays the response of the output. On the next slide, we will graphically demonstrate how this delay makes output value dependent on the direction of change of the input. You will be able to visualize that because of this dependence, a single input value can yield two different output values depending on whether the specified input was reached by increasing values or decreasing values. For greenhouse applications, hysteresis effects are typically insignificant due to its small error. For example, a platinum thermistor with a 200 degrees Celsius range can have a hysteresis error of 0.2 degrees Celsius. What size error becomes significant? I would say plus or minus 1 degree Fahrenheit in the range of 40 to 100 degrees Fahrenheit for air temperature monitoring, and plus or minus 2 degrees Fahrenheit for hot water temperature in the range of 40 to 212 degrees Fahrenheit. The ideally plus or minus 2 degree in the 40 to 212 degree Fahrenheit range is 1/90th or about plus or minus 1%. In reality, however, a sensor range is much wider than the temperature range of interest. For example, a thermistor could have a sensing range of 270 degrees Fahrenheit. The plus or minus 2 degree Fahrenheit measurement accuracy requirement requires plus or minus 0.1%. It is important to note that hysteresis typically increases with rapid condition changes. Sensor users should be aware of the percent error due to any hysteresis. This information is typically reported by the manufacturer as a part of the sensor specifications. For example, Lycor and Apogee use silicon detectors rather than selenium detectors and claim that this eliminates hysteresis effects. A humistor from Bichet claims a 3% hysteresis error over its 10 to 90% relative humidity range. This is an error of 2.4%. A type K thermocouple can display hysteresis errors if brought to extreme temperatures, such as 1000 degrees Celsius, that are never seen in the greenhouse. Now we will graphically examine hysteresis. We will use a temperature sensor as an example. As I walk through a temperature increase followed by a decrease, observe the graph of sensor output versus sensor input or actual temperature. At first, increasing the temperature results in no output or display change due to hysteresis and resolution of the sensor. When the temperature increases enough to overcome instrument friction, the display responds linearly to changes in temperature input. When the temperature increase stops and then declines, hysteresis and sensor resolution delay a change in sensor output. When the temperature decrease is large enough to overcome instrument friction, the output or display responds linearly to changes in temperature input. As you can see from the graph, the sensor input value A is represented with two different output or display values depending on if the temperature was increasing or decreasing. We are now moving on to the fourth objective. Explain why multiple data points may be required for proper calibration. If user calibration is possible, the number of required data points should be specified in the sensor's literature. The number of points required depends on the sensor's measurement characteristics. If a sensor has a linear response, and if the y-intercept is 0, calibration will require 1 data point. If the y-intercept is not 0, the calibration requires 2 data points. If a sensor has a nonlinear response, more than 2 data points will be required for calibration. Higher order systems will require the most data points. The more data points, the better the calibration will be. The number of points is decided by the economics of the calibration process. Objective 5 is to identify quick check values for light, humidity, temperature, and CO2. Here are some values that can be used to check sensor readings. The purpose here is a quick, convenient check of the measurement devices, not a precision check. These values are used just to make sure the sensor readings are acceptable. According to the Handbook of Turf Grass Management and Physiology, light, specifically the photosynthetic active radiation, or PAR, should be about 2,000 micromoles per meter squared per second at solar noon on the summer solstice and a clear sky. Photosynthetic active radiation will be measured with a quantum meter. If the sensor is covered, it should read about 0 micromoles per meter squared per second. For relative humidity, a convenient check is the use of saturated salt solutions. At any temperature, the concentration of a saturated solution is fixed and does not have to be determined. By providing excess solute, the solution will remain saturated even in the presence of modest moisture sources and sinks. When the solute is still present as a solid, there is saturation in the solution. The saturated salt solution, made up as a slushy mixture with distilled water and chemically pure salt, is enclosed in a sealed metal or glass chamber. Greenspan identified the relative humidity of air over a saturated table salt or sodium chloride solution at about 75%. When there is a heavy mist outside, the relative humidity is about 100%. For temperature, a well-stirred crushed ice bath is 32 degrees Fahrenheit or 0 degrees Celsius. Boiling water is 212 degrees Fahrenheit or 100 degrees Celsius. For carbon dioxide, according to the National Oceanographic and Atmospheric Association, ambient levels have reached about 400 parts per million. Ambient levels fluctuate by season, proximity to combustion systems, proximity to animals, and proximity to people. Accuracy is typically about plus or minus 50 degrees parts per million. Nonetheless, ambient levels are a good quick check. Now that we have a list of quick check values for different sensors, let's explore an example of performing a quick check with a CO2 sensor. A CO2 sensor is checked against either ambient levels or a 400 part per million calibration gas, and it reads 400 parts per million. Does this mean that the sensor is properly calibrated? The answer depends on whether the sensor response is linear, linear with a non-zero y-intercept, or nonlinear. If the sensor is linear, one calibration point is sufficient, and therefore it can be assumed that this sensor is properly calibrated. If the sensor has an offset, or a non-zero y-intercept, 2 calibration points are needed. This sensor, even though it reads correctly at 400 parts per million, may not be properly calibrated. The sensor may not read correctly at 1000 parts per million, for example. If the sensor is nonlinear, multiple calibration points are needed, and therefore we cannot assume from the quick check that the sensor is properly calibrated. Also, there are other factors. Carbon dioxide sensors, in particular, are sensitive to temperature and moisture content. For example, a publication by Viacella states that at standard atmospheric pressure and at 25 degrees Celsius, one of their CO2 monitors would read 1000 parts per million with an input condition of 1000 parts per million. However, decreasing the temperature by 5 degrees Celsius could change the output to 1017 parts per million. The moral of this slide is that quick checks can be helpful, but do not guarantee that a sensor is or is not properly calibrated. As a sensor user, you should study the sensor literature and specification sheet and determine whether the sensor response is linear, linear with an offset, or nonlinear. After installation, observe sensor performance regularly to ensure that readings are accurate and precise. Perform scheduled calibrations on an annual basis or more frequently if needed. Use a reliable meter as the standard for all calibrations. To make sure that sensors work accurately, consider environmental parameters that may influence the measurements, such as exposure to direct radiation, radio frequency interference, uneven or unmixed air or water, distance to heat sources or sinks, location of heating, cooling, or dehumidification devices, and random signal noise. Thank you for viewing.